category of phase diagram, you will learn how what is the what is the eutectic system and how we interpret the materials behavior, solidification for this kind of alert that having eutectic system. So you should be able to read and interpret eutectic phase diagram, write a reaction for eutectic transformation for either heating or cooling. So eutectic reaction is a three-phase reaction, three phases, okay, by which on cooling, a liquid, during the cooling, okay, liquid transform into two solid phase at the same time. Okay, for example, liquid alloy becomes a solid mixture for alpha and beta at specific temperature rather than over a range of temperature. Remember, for the alloy, if you are still remember last time, okay, when we differentiate between the cooling curve for pure metal and the alloy. They are different, right? For pure metal, a temperature versus time, the cooling curve will show a horizontal, a constant temperature, okay, during the transformation during the two phases of liquid plus solid. Okay, this is pure metal. You will only see one constant temperature, which freezing temperature and as well as the melting temperature. However, for the alloy, okay, remember when we add 10% of nickel in copper, 20%, 30%, what we can see during the transformation from solid to liquid, from liquid to solid upon cooling, you may see the temperature gradient between T1 and T2. What is T1? T1 is the beginning of solidification, means solid begin to form. Okay, and T2, what is T2? Solid end. Okay, call it a solidus point. This one is liquidus point. Okay, you can see the gradient temperature. Unlike an alloy, pure metal show a fixed, a constant temperature. All right. However, for the eutectic reaction, okay, three phases reaction means it's involve two solids and the liquid. Okay, involve three phases. Okay, for this one, it is liquid and solid. Okay, but this one is involved three phases, which is liquid plus solid 1 plus solid 2. There are three phases for the eutectic at a constant temperature. Okay, liquid alloy becomes a solid mixture of solid 1 and solid 2, which is alpha beta, we name it, at a specific temperature. Okay, constant temperature. Okay, rather than over a range of temperature for the alloy. But still, we talk about alloy for this case. Okay, except for it is in a eutectic reaction. All right. All right. For the experiment, okay, how they measure, they come up with this kind of eutectic reaction. Okay, 11 composition were used, okay, to construct the phase diagram. 11 composition were used from pure bismuth to the pure tin in step of 10%, where all the composition were measured in weight percentage. Okay, so means that the percentage, the increment by 10% is a weight percentage. Okay, weight percentage. Okay, we write like this. Okay, and this is the setup for the experiment. And then this is the result from the experiment. Okay, what you can see, this one is a uh, red. Okay, this is yeah, it's supposed to be a constant temperature. No, constant. Okay, this is a constant temperature, and this one is a range of temperature. Okay, during the transformation, a range of temperature, a range of temperature. But this is alloy 1, alloy 2, alloy 3. Okay, the green, this one 50%. Okay, for the 50%, it is a gradient temperature, but this one is not. But about between 60% and 70%. Okay, between 60% and 70%, you can see that the cooling curve is almost having a transformation phase at a constant temperature. Okay, for 60 and 70, almost. Okay, so from this data point, okay, from this data point, they found out that it is somewhere, okay, for this result, they interpret that at this 60% of bismuth, 60% is a constant, okay, constant. Okay, this one means green gradient temperature. So 60% having constant temperature, okay, but the rest, the red line is a pure bismuth. The purple line here is a pure, um, no, pure bismuth. Uh, this is pure tin. Okay, this is pure bismuth. Okay, so it is only one single temperature, right? So what about the 10% of bismuth? 10% of bismuth shows a gradient temperature. Okay, from T1, T2. Okay, so this is T1 and T2. So meaning that this is a liquid phase, this is liquid plus solid, and this is solid of the 10% bismuth in 90% tin. Okay, and similarly to the 20%, okay, 20% of bismuth. Okay, this is liquid. This is the beginning of solid formation. Where is it? This point, T3, and this is T4. Okay, this is T3, and then this is T4. All right. Okay, look at this. Okay. Um, the line in yellow, this is 10%, 20%, and 30%. Okay, the line in yellow, look carefully, this line. Okay, let me zoom in a bit. Okay. All right. The yellow line. Okay. If okay, please focus at the yellow line. Okay, this yellow line, if you look carefully, this temperature is reduced to up to this point, and then you can see a horizontal line like this. Okay, and then it reduces the temperature. Okay, this one is similar to the other alloy behavior, like this one. Okay, oops. All right, and this horizontal line similar to the pure metal. Okay, it shows a constant temperature. Okay, this one is time. So meaning that over the time, the temperature does not change from point A to point B. Okay, over the time. Okay, meaning that after some time, you can see a constant temperature. Okay, what does it mean? This constant temperature. Okay, this constant temperature Okay, label as similar T4. Okay, for the yellow is 30%. Okay, this is T5, and then this is T6. T6 and T4 at the same point. Look carefully, right? This point A to B, this point, and this point, constant at the same point about this temperature. Okay, so what we get, okay, for all different composition of alloy, you can see a horizontal line like this. Okay, where you did not find this at the complete solubility phase diagram. Okay, the previous the type number 1 of the phase diagram. Okay, this limited or partial solubility phase diagram, um, you can see the you can see the eutectic reaction. Okay, eutectic system can be observed here. All right. So the rest is similar, meaning that the other percentage for 40, 50, 60, 70, 80, 90, and 100% of bismuth. Okay, for the 60%, you can see a constant temperature. So it will show only one. So what does it mean? Meaning that when the temperature reduces at this constant temperature, it will change from liquid to the two phases below. Okay, two phases below. Okay, what is the phase? Okay, this is example bismuth and stannum system. Okay, unlike the previous slide, this one you can see the increase of amount stannum. Okay, if you read from right to the left, you can see the increase of what percentage of bismuth. Okay, so either way, it can be both sides as long as you can obtain the right information. Okay, so when we construct this phase diagram based on the cooling curve that we obtain from the experiment, okay, what we obtain is a line like this. Okay, the first line similar to the complete solubility system, where we call it liquidus. Okay, so what is a liquidus line? It's a boundary between liquid and the solid and liquid phase. Okay, that's defined liquidus line. What is solidus line? Solidus line is a limit separating between solid and solid plus liquid line. Okay, for alpha solid, and this one is for beta and alpha solid. Beta, okay, beta and alpha solid, right? So solidus and liquidus. Another one, we have solvus. This is solvus. What is solvus? Solvus is a solubility limit of one solid phase, which is alpha, to another different phases. Okay, different region. In this region, is contained alpha plus beta. Okay, how we get alpha plus beta? It is alpha coming from the left region and beta coming from the right region. So in the binary system, okay, we write a phase, we label a phase alternately. Okay, from alpha, next is alpha plus the next phases here. For example, the next will be beta, so in between is alpha plus beta. If you look at under microscope, you can see two different what we call it, two different color of microstructure. One is darker to another, right? So means there are two phases. I have showed to you several microstructure image where we can see the different gray color. Okay, one is darker compared to the other. So meaning that they are different in terms of the phase. So the mixture means it's contain alpha and beta. Okay, if you see only one single color, so mean it's only one phase. Maybe it is alpha or maybe it is beta. So in the phase diagram, when we label the phase diagram like this, you may see that if this is alpha, the next the next region will be alpha plus beta. What about this region? Okay. For example, this region, this triangle region. Okay. So it is alpha from the left. Okay. And liquid from the right. So the region here will be alpha plus liquid. Okay. Um, so for this region, okay, this region in the first diagram, okay, is contain liquid plus beta. How we label this one is coming from the left liquid, and from the right is beta. Okay, so this is how this is the system for the phase diagram. So the label, there is a liquidus and solidus line, even there are solvus line. Okay, so now go back to the eutectic point. Eutectic point is a point where you can see that the transformation from liquid to two different solid at one single temperature. Okay, constant temperature. If you look into the phase diagram, you see something like this. Means something like this means okay. So if you can see the wish, okay, if you can see a V shape like this, okay, where you can see one face transform into two different faces, or maybe two faces transform into one single face at one particular temperature. That one is a isothermal reaction. In this example, okay, liquid transform into alpha plus beta. We call it eutectic. Okay, if you cool it down, you will get liquid transform into two solid phase. If you heat it up, this alloy, if you heat your alloy into liquid, it will transform into liquid phase at one temperature, a constant temperature. Okay, so okay, now what is alpha? Alpha is defined as solid solution. Okay, where in this solid solution, it rich with bismuth, with some titanium atom inside it. Okay, so the crystal structure of bismuth, okay, is a different compared alpha is different from the beta. Okay, solid solution of okay, beta is solid solution that rich with tin. Okay, if you look at tin composition is between 80 to 100% tin. Okay, stannum. But alpha contained, okay, about only 5% of tin. Okay, the rest 95% is bismuth. Okay, and the crystal structure for both alpha and beta is
kalau
different.
data mostly yang ni rasanya ada masalah lagi ke? Sebab saya rasa diorang dah communicate lah untuk data view.
Okay, so if we pick any alloy, okay, for the bismuth stannum system, any alloy, for example here, 2% stannum alloy, okay, 2% stannum, 98% bismuth, okay. Okay, let's say this is your alloy. All right, for this alloy, okay, if we sketch the phase diagram, okay, and the phase diagram, the cooling curve, you may see that there is a phase transformation from temperature 300 degrees Celsius or above 300 degrees Celsius to the 260, okay, this point. right? Which is 260 degrees Celsius. Okay, what is temperature? What happened at this temperature is a solid solution began to form. Okay, solid solution of alpha. Okay, alpha solid. Okay, and when the temperature keep reduced until temperature what temperature? Okay, until this temperature. Okay, suppose though there are two different temperature. Okay, all right. The 200 about 230. Okay, this point 230. Okay, you can see that alpha will complete. Yeah, let's say this is 230. Okay, at this point, um, what you can see is only alpha. Okay, from this point to this, from this temperature to this temperature, it is only liquid. From this temperature to this temperature, it is a liquid plus alpha. And then from 230 or 225 degrees Celsius, okay, there are only one single temperature. Okay, and then the first 10 years continue, okay, until 100 sorry salah. Okay, so right, now it's 160 lah. This is about this is 260 for this point. This is supposed to 225, and it keep reduce temperature. Okay, this point there's a liquid plus okay, sorry. Okay, this is about 100. This solution ends. Okay, it is about 125. Okay, sorry, 125 degrees Celsius, where the solid solution of alpha ends, and single solid solution. And for this, it is a solid mixture, which is alpha plus beta. Okay, so this is alpha plus liquid. This is liquid. So there are two temperature, which is 260 and 125. Okay. Plus liquid. Okay. At this point, somewhere this point, it is about 225 degrees Celsius. Okay. So the temperature shows a gradient temperature. Gradient temperature means that from 260 until 125, it shows a changes in the liquid plus alpha and then single alpha. And then at this point, okay, which is okay, if we look at the phase transformation here, point number one, let's say it is above 271 degrees. Okay, so this point, okay, point number one, it is only liquid. You can draw like this. Okay, and then point number 2, this is number 1, this is number 2. Okay, for point number 2, what is the phase present at this temperature 2? Okay, let's say this temperature 1 is above 271 degrees Celsius, and temperature 2 is equal to 250 degrees Celsius. So what is the phases present in this point? Point number 2. Anyone?
Mixture, Doctor.
Apa dia?
Is it mixture?
Yeah. What mixture? Mixture of what?
Liquid.
Yes. Okay. You can draw like this. This is alpha, and this is liquid, and label it as a liquid. Okay, the mixture. All right. And what about point number 3? Okay, let's say the temperature is temperature 3 is equal to 155 degrees Celsius. How to draw the microstructure? This is microstructure. This is microstructure. Okay. So what is the microstructure for point number 3, where the temperature is equal to 155 degrees Celsius?
That's alpha.
I'm sorry,
That's alpha.
just alpha. So of course, yes, it is only one alpha. So how to draw it? It is like this. It is solid. There's no more liquid. Okay, only alpha. What is alpha? Alpha is a solid solution. It is solid. Look at this, solid, right? So the drawing of a solid. Okay, remember, at the point number 2, you can see the nucleus and the small crystal of a small grain of alpha. So when it grows larger upon the reduction of temperature, okay, so it will form a grain boundary, okay, at the interface between the grain. So you must draw a grain boundary like this. So this is alpha, 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 all are alpha solid. Okay. So okay, all right. When the temperature further reduced to the room temperature or temperature lower than 100 100 berapa 125, okay, let's say temperature equal to 85 degrees Celsius, okay. So what does it looks like? Okay, so what about the microstructure at point number 4? Right, for this answer, okay, please think what is the microstructure, and try to sketch by yourself, and then later I will create the submission link for this short assignment. What is the microstructure for the point number 4? Okay, it is room temperature. The temperature will be similar to the room temperature, where it is contained only 2 phases. So try to sketch. I will leave it to this answer to you, and try to think what is microstructure for this temperature. Okay. Now next is just now we talked about 2% of 2% of sternum inside the bismuth. Now this is another alloy. Okay, another alloy which is still bismuth plus sternum, but for this alloy, it's contain 40%, 44% of sternum. Okay, 44% of sternum. Okay, this 44% of sternum fall exactly at the eutectic composition. Okay, this is eutectic composition. Eutectic composition. What is eutectic composition of bismuth sternum alloy? It is 40%. sternum. Okay, bismuth 40% sternum, 44%. Sorry. Okay, when we talk about bismuth 44% sternum, it is eutectic. Okay, it is eutectic. So, eutectic or non-eutectic, eutectic or solid solution alloy of bismuth sternum, they are different in terms of the microstructure. Therefore, they are different in terms of the mechanical properties. So that's very important when you want to design an alloy, or you want to design, you want to select your material for your design. Make sure you know the microstructure. How to determine the microstructure? Based on the composition. Okay, for example, like this one, it is eutectic. Okay, eutectic point. So for eutectic point, it consists of one, transformation temperature. Okay, isothermal solidification temperature. Isothermal means one single temperature that allow the transformation, a complete transform from liquid to solid. Okay, so liquid into alpha plus beta. Okay, right. Based on the experimental observation, many eutectic alloy, when we talk about eutectic alloy, they have alternating structure of alpha and beta lamella. Okay, alpha and beta. All right. When they start to form a solid, they tend to arrange themselves in alpha and beta, layer by layer. Lamella is a layer by layer between two phase. Okay, so it's happened at this point. Okay, eutectic temperature composition. Okay, this is real microstructure that we observe under scanning electron microscope. Okay, if you look at this microstructure, all right. So you can see there are two different color. All right, the color represent the different composition of element inside. Okay, so let's say this is beta, and this is alpha. Okay, alpha and beta, they are different. They both contain bismuth plus sternum. Okay, both are bismuth plus sternum, but the composition of sternum and bismuth inside each phases is different. Okay, maybe at this point sternum has 60%, and this one is only 40%. Maybe for this one, bismuth is only 20%, and sternum is 80%. Okay, so that's the reason you see the different color, because the different color represent their response to the electron sighted by using the microscope. Okay, so less than and high density of the electron inside the atom, okay, shows the weight, the atomic weight of the element. So the more lighter elements, the darker we will observe under microscope. Okay, that's the principle. Maybe this is out of the scope of your course, but this is what we observe layer by layer. Okay, layer by layer, we call it lamella. Okay, lamella. Okay, we observe, and we can observe this structure if it is passing through this eutectic temperature. Okay, from XA to X beta. Okay, so meaning that you can get this microstructure if you alloy within this range. Okay, so now we talk about exactly this composition. Okay, transformation occur at this single temperature, completely transform into a solid that contain 100% of lamella. 100% lamella. If you have alloy at this composition, it's not 100%. It's contained because it's passing through this region, right? So meaning that there are the first formation, the premier formation of alpha, okay, before they obtain the lamellar structure. Okay, unlike this kind of alloy, the eutectic alloy, you will obtain 100% lamellar structure. Okay, so the microstructure, how to draw the microstructure? It's very simple. Start from the point 1 is a liquid. Okay, point 2. Okay, at this point 2, you can see that inside the liquid, there are the formation of lamellar structure. Okay, until it's completely yeah, the point number 2 is very complicated because we don't know where's the time for this transformation. For example, the cooling curve, temperature versus time. Okay, it can be this point for this point. It can be here, 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 or here. They are different in terms of the growth for the lamella structure. But up until this point, okay, you can draw whatever the size, but it's missing between liquid and the lamella structure. However, at this point, okay, the last point is consists of a lamella structure. Okay, a lamella structure. You can draw like this. Until you confuse me. Okay, so this is liquid. This is a lamella structure. Okay, like this. Okay, the nucleation of lamella and the grain inside the liquid. Okay, right? Microstructure of eutectic composition. See, you can see the lighter, the darker, they are arranged side by side. Okay, some of them are large, some of them are very fine lamella layer. Okay, but all of them are in the lamella structure. Okay, right. This one I have slightly explained just now. Okay, for this kind of alloy, for example, 20% of sternum inside the 80% of bismuth. Okay, look at this cooling curve. Okay, the cooling curve we construct point 1. Okay, temperature 1. Temperature 1 is here. And then temperature 2 is a eutectic temperature. It is temperature 2 is here. Okay, so as long as it's passing through this horizontal line, this is eutectic temperature. Eutectic freezing or eutectic temperature. Okay, whenever your alloy falls between this region, meaning that the composition between I don't know what is it 5% until 80% of sternum. Okay, let's say for this one is 20%. It is between 5 until 80%. So it's passing through this horizontal line, eutectic temperature. So there are horizontal one single constant temperature transformation. Okay, right. What happened is between this temperature, melting temperature, the temperature where it's melt the alloy, okay, where it is liquid only in this phase. All right. At temperature 1, from liquid it transforms into liquid plus, what is it? Liquid and what? Apa dia? Lemaunya. Apa dia? Liquid plus alpha. Okay, between temperature 1 and temperature 2. Temperature 1 and temperature 2. Liquid plus alpha. And then, until this point, okay, there are still remaining liquid. Okay, remaining liquid will transform into alpha. Okay, just now we have alpha already. So in this region, there are alpha plus liquid. Alpha plus liquid plus lamella. Okay, lamella. There are 3 phases at this region. Okay, at this constant temperature until liquid completely transform into lamella. So the primary alpha that form within this region, okay, this is a point where primary alpha will form, and then at this point there's no more single phase alpha. What happened at this single temperature is the liquid will transform into lamella structure. So at this point, what happened is only alpha, which is primary alpha, plus lamella. Okay, lamella. What is a composition of lamella? It is alpha plus beta in the lamella structure. So in total, it is alpha plus beta. Okay, so it is like this. Okay, point number 1, microstructure of liquid. This is 1, 2, 3, and 4. Okay, liquid. And point number 2, inside the liquid there are, okay, primary alpha, okay, and it's grow upon a reduction of temperature. So now alpha, when it reach point number 3, alpha will stop to form. And what you can see at this point, the lamella, this is primary alpha. Okay, you can see that lamella will form, okay, lamella. Okay, alpha will remain, okay, like this. And then at the end, what you can see is this is alpha, and alpha. It is surrounded by a lamella structure. Okay, this is primary alpha. This is lamella, alpha plus beta. Okay, so this is your lot. Okay, alpha and beta different in terms of mechanical properties. Okay, why? Because beta is rich with stannum, rich. Okay, and then for alpha is a bismuth rich. Okay, bismuth rich solid solution. So of course, if you have more stannum, you have majority the mechanical properties of stannum. If you have alpha, you have a majority properties that dominated by bismuth. Okay, however, okay, when we have a lamellar structure like this, okay, it is another story. Okay, the properties is influenced by the physical structure of the alpha and beta. Okay, imagine habuk kayu. Okay, the wood powder. Okay, wood powder, you make a solid structure, and the solid wood. All right. The properties of one solid structure of okay, you have this solid wood, and you have a structure like this as a wood powder. Okay, right? They are different in terms of mechanical properties. Okay, if you have a wood made of a solid wood and a wood made of the chip or wood powder or apa ni, habuk kayu wood powder, and then another is you make a lamellar structure, papan lapis. Okay, consists of wood powder and the solid wood. Okay, this is solid wood. This is a wood powder. So they are different in terms of the properties. This one is because of the design structure, layer by layer of the plywood. Okay, consists of solid wood as well as the wood powder. Okay, the wood powder as a single phase itself, it doesn't strong as a solid wood. So they are different of composition in terms of the material composition. They will produce a different mechanical properties. So in terms of by understanding the properties for 3 different phases, okay, one is a single alpha, another one is single beta, another one is lamella alpha plus beta. Okay, by understanding their mechanical properties, you can design your alloy, which properties that you want. So each different composition, okay, different composition will produce different mechanical properties. So you must know which one is the best that suit your design. Okay, and not because of that, the melting temperature. The melting temperature, they are different. The eutectic alloy is the lowest melting temperature. Okay, eutectic alloy. If you have 44% cerium in the bismuth, so it is the lowest melting temperature. Okay. All right. For this kind of alloy, okay, hypoeutectic, okay, hypoeutectic composition. If you have bismuth, cerium, composition, hypo is a this alloy, okay, this alloy that consists of between the region of eutectic fall on the left side. We call it hypo. Okay, this one is hypo eutectic, but this one is hyper eutectic. So whatever we discuss now, okay, where the composition between 5 until 44% of bismuth, it is known as hypoeutectic composition. So what you can see, okay, this is one single phase, okay, maybe it is primary alpha. This one is another phase, which is lamella. If you zoom in, you can see that the lamella structure like this. Okay, so lamella, layer by layer of alpha plus beta. Okay, right. Similarly to hypoeutectic, okay, for hypoeutectic, at this point it begins to form primary beta. Okay, unlike this alloy, you may see primary alpha. Okay, similarly, alpha beta will grow larger, and then at this point it start to transform the liquid, only liquid. Okay, yang dah jadi solid tu dah jadi primary beta tu is that's it. And then the remaining liquid will transform into lamellar structure. Okay, until completely no more liquid at this point, and then what you get is a primary beta, at room temperature primary beta plus lamella. Okay, you can sketch by yourself the drawing. This is hyper-eutected, slightly different. What you can see is a primary beta. Okay, consists of large portion of the area, and at this grain boundary is a lamellar structure. Okay, for this kind of alloy, where tandem rich alloy that does not contain lamellar structure, because it is beyond this limit. Okay, no lamellar structure. Okay, why? It is not falling onto the horizontal line, which is eutectic temperature. So between this point to this point, you can obtain the single phase of solid. After this point, where is it? This point. Okay, 139 degrees Celsius. No, not 139. Okay, solid solution of is supposed to be about 85 degrees Celsius or 90 degrees Celsius. Okay, single solid solution will end, and then what happen is the formation of alpha. Okay, so similarly to the alloy that's lower than 2%, lower than 5%, for example 2% just now, standard. Okay, you can sketch the microstructure. Right, this is beta solid solution, and at the grain boundary, why grain boundary is alpha? Because right, why I said this is beta, because remember when it's starting to form a solid at this point, what happens is beta will form first, and it will grow larger, okay, until it will obtain one single phase of beta. So when you obtain alpha basically will form at the grain boundary. This is alpha. Okay, grain boundary. Why? Because grain boundary is the weakest point, the most less than atoms and irregular non-oriented atoms, atomic arrangement at that particular region. So diffusion may easily occur. Because of the diffusion, new phase will form, which is alpha. Okay. All right. I will continue this part on the determination of the phase composition to the next week. For tomorrow, we have tutorial class. I'm going to do the exercise for the test one. Okay. For your information, our test one is not similar to the previous test one because of yeah, we faced so many integrity issue for the final exam last semester. So for this semester, we will start to have open-ended question where it is actually a take-home exam. All right, you don't have to stay online for 3 hours or 2 hours or 1 hour test. What you need to do, you will be given to answer an open-ended question. It is 2 questions covering 4 topics that we have learned in the 5 topics. I'm sorry. Okay, meaning excluded this space diagram topic. So what you need to, you can search the information from any resources, but you have to answer by your own words. For that, before submit, you need to check the similarity. You need to type by using Microsoft Word and check the similarity of your answer in the Turnitin system. Okay, for tomorrow, we are going to do some practice on how to answer the open-ended questions and how to submit to the Turnitin. Okay, I think that's all for today. Before I end this class, I will once again share the attendance for today.